Hello and welcome to the Absolute State of Science Part 2. I'm your host. In this episode, we're going to pick up right where we left off on Episode 1, but because you read the title and you know we're going to talk about black holes, we might as well talk about them and get them out of the way. Black holes, just like geocentrism, make perfect sense. We know that black holes must be in the center of most galaxies, because for galaxies to maintain this shape, the mass required must be so dense that it makes a big enough curve in the fabric of space-time. And we can't see black holes because space-time is curving so hard that light can't escape it. But before we get sucked into the entire black hole topic, there is something else about space that we really need to talk about first. And to talk about it, I want to invite you to my virtual museum that I built here. I'd like to direct your attention to Exhibit A. It's something simply called plasma. So I'm not sure if you know this, everyone who watched Part 0 knows this, but 99% of the universe, the entire universe, is made of plasma. Plasma is not a gas, liquid, or solid. It is the fourth state of matter. Plasma often behaves like a gas, except that it conducts electricity and is affected by magnetic fields. On an astronomical scale, plasma is common. The sun is composed of plasma, fire is plasma, fluorescent and neon lights all contain plasma. Plasma has many names. Sometimes it's referred to as a hot gas, or ionized gas, or charged particles. Anytime you see something like that, it's talking about plasma. So let's look at a plasma arc. Plasma, the ionized gas, when a gas is heated above 17,000 degrees Fahrenheit, electrons are free to move. The gas conducts electricity. So heating a gas to 7,000 degrees is one surefire way to get plasma. However, plasma is a lot more interesting than that. Just like how we have 4 states of matter, plasma, all by itself, actually has 3 different states that it can be in. And the first state or mode is the invisible mode. It's when the plasma has very, very low current, and it will exist in a sort of dark current mode. We see this in the ionosphere, in the atmosphere, very low current. But as you increase the current, the previously invisible plasma will start to generate light. And this can be seen in the northern lights and those cute little red sprites that we see every now and again. So these 2 glowing, energetic, atmospheric phenomenon are an example of the second mode of plasma. Glow mode. We can also see that in neon signs and plasma balls. But if glow mode isn't bright enough for you and it's not doing, it's not doing it for you, you need something with a little kick to it. It's when you jump it into the third gear, or third mode. Arc mode is what that's called. So that's what happens when you keep heating it up and you keep adding energy to it, it starts to arc. This can be found in lightning and electrical arcs. And just remember, the stronger the current, the brighter the plasma. So let's direct our attention to Exhibit B, space plasma. So under the Common Plasmas section of Wikipedia, it says space and astrophysical plasmas. First one on the list is stars. Then we have the interplanetary medium, so the space between planets, the interstellar medium, the space between star systems, and the intergalactic medium, the space between galaxies. So pretty much just about all the black that you see in space, all of that is filled with charged particles, or ionized gas, or plasma. So when we look in space and we see all this dusty, cloudy, glowing stuff, that is plasma, which is not gas. As you can see here, comparison of plasma and gas phases. The electrical conductivity of a gas is very low. The electrical conductivity of a plasma may be treated as infinite. Very different substances. And so since we have plasma in space, we have found the universe's highest electric current. We have found twisted magnetic fields around galaxies. And the really cool thing about an electric current and finding one in space is that where you have an electric current, by default, you have a magnetic field. Can't separate them. If all stars are made of plasma, and our sun is a star, does that mean that our sun is electrically driven? And you're saying no. Dude, what are you talking about? Of course not. Of course not. That's impossible. In the article you just read from Wikipedia, it says plasma's heated by nuclear fusion. We already know how the sun works. Well, let's just check out our next exhibit here and review that. So, the sun, as we understand it, is a giant nuclear campfire in space. It's the densest thing in the solar system, and that's how it keeps everything in orbit. It has a super hot, hella dense core and radiates heat out from the center. And when I say it's a nuclear campfire in space, I'm talking fusion, as I already said, not fission. The bombs are fission, fusion's the sun. And if you aren't familiar with nuclear fusion, well, did you know that the 3 largest cities in the US are powered by nuclear fusion? Oh, you've never heard that before? Because I just made that up? Yeah, turns out fusion is a process that no one on Earth has ever reproduced. It's a theorized, unrepeatable phenomenon. The joke about nuclear fusion is that it's 30 years away and always will be, said the head of the UK's Atomic Energy Authority. A nuclear fire that is perpetually and consistently exploding outward at the exact same speed that it's being pulled inward by gravity so that it maintains a perfect sphere and has 11-year cycles. Why would an explosion have an 11-year cycle? And it works in a way that we've never successfully reproduced. That makes perfect sense, just like the geocentric model. So another thing about the sun is that it's kind of like a Katy Perry song. And what I mean by that, well, let's just look at the different temperatures across the different layers. So let's look at the corona, which is the outermost layer of the sun. It's the fluffy part, not the surface. So the corona is around 1,000,000 degrees, which is pretty freaking hot. And as we get closer to the core, it's actually colder. Yeah, the surface is only 6,000 degrees. Like, that's it. It's like, think about that in dollars and how big of a difference that is. And that's not even the coldest part. The absolute coldest spots on the sun are called sunspots, and they're like 4,000 degrees. And when I first heard about those spots, I thought it was like those little lava pillows that the One Ring lands on at the end of Return of the King. And no, that's not what they are at all. So if we look really closely and we look at this in the visible light spectrum, we can see that the penumbra, this part right here, actually seems to fall inward towards the core. It looks like a hole, and it's the coldest spot. It's just interesting because you would think that if the core is 15 million degrees and the outer layer is 1,000,000 degrees, that the surface would be somewhere in between those two. Let's move on to Exhibit C, MagnetoHydoDynamics. Yes, a very common word that I know everyone is totally familiar with. This is the study of the magnetic properties of electrically conducting fluids. So what we're seeing in the video here is an external current flowing through a tub of salt water with flakes of rust floating in it. Salt water is, of course, a magnetofluid. Another magnetofluid is plasma. So, as you can see from the video, it doesn't look anything like a galaxy spinning or rotating or anything like that. An experiment demonstrating the effects of an electric current flowing through a magnetofluid makes the shape of a galaxy. Galaxies are made of a magnetofluid, and galaxies are known to be magnetic. And a magnetic field is known to result from an electric current. So, yeah, by the way, the sun. Yeah, it turns out that's actually a magnetohydrodynamic system that is not well understood. So, yeah, interesting. Oh, speaking of things that aren't well understood, let's go to our Exhibit 0G right here.
This is Star Talk.
What is gravity?
You have no idea. Okay, next question.
Wow.
No, here's the difference. We can describe gravity. We can say what it does to other things. But when you start asking, like, what it is, I don't know. So to say, what is it? I think Einstein, in an Einsteinian answer, we would say gravity is the curvature of space and time. And objects will follow the curvature of space-time, and we interpret that as a force of gravity.
So, okay. Oh, and while we are looking at spinning things, here is what static electricity looks like in a 0G environment. These are water droplets orbiting a knitting needle charged up with the paper towel on the International Space Station. It definitely doesn't remind me of planets orbiting or anything like that. So anyway, just more food for thought. So now, let's move on to our last exhibit, Exhibit Q. So now that we know a few things about plasma, and we understand that long-range electromagnetic fields dominate the behavior of plasma, do you think that maybe the electromagnetic force is responsible for the motions of stars and galaxies? Or do you still think black holes and curvatures in the fabric of space-time are responsible for the motion of stars and galaxies? So if you think black holes, why do you think that? Where did you learn about black holes? And where did the person who taught you learn about black holes? I just find it very strange that a person would look at this phenomenon, a galaxy, literally the brightest thing outside of the sun that you've ever seen in your life, and your first guess would be, it's probably something so dark and dense that light can't even escape it. Well, we can trace that entire line of thinking back to here, the solar eclipse of May 29th, 1919. That's the day that Einstein's theories leapt off of the chalkboard and into the real world, when we observed the bending of light during a solar eclipse. Einstein said the light was bending through the fabric of space-time. But now we know that the sun's corona is made of ionized gas, or plasma, and we know that plasma refracts or bends the light, and we know this because the ionosphere refracts light. And we know that the refraction or bending of light has absolutely nothing to do with the fabric of space-time. So this phenomenon that we see when we look out at the stars all the time, gravitational lensing, could very easily be light refracting through the astrophysical plasma in dark current mode. And now I know that the general relativity paradigm is perfect and it has an answer for every question that you could ever ask about space. The math all checks out, it matches the observations, and it could probably stand as the popular belief system for the next 1,000 years. I mean, the geocentric model stood for 1,000 years, and that was because it provided answers to questions people asked. It was a complicated mess, but it worked well enough. So just because your paradigm has an answer doesn't mean it has the correct answer. And a good way that we try to find the correct answer is we use tools like Occam's razor, which says that all things being equal, the simplest solution tends to be the best one. So I have to ask, if Einstein was alive today and he saw all the evidence, do you think he would have reached the exact same conclusions he did 100 years ago? And my last question is, why are you defending general relativity? I mean, like, at the end of the day, do you really want space to work that way? Like, do you really want to assume that the sun is a nuclear fusion campfire that's eventually going to burn out? Do you want the inevitable heat death of the universe? Why are you fighting for super depressing theories to be right? What is your motivation, and who does that help in the long run? Like, even if both paradigms are wrong, I'd pick the wrong and happy one over the wrong and sad one. So that brings us to the end of parts 0, 1, and 2. Thank you so much for watching. I think that this is the last time I'm probably going to bring up Einstein in general. We're only going to be talking about space from the much happier paradigm from here on out. So please subscribe. Part 3 should be out pretty soon, probably. And in that episode, we're going to talk about the local solar system and talk a little bit more about the theory and explain a little more what's going on. So that's going to be super fun. So thank you for watching. Have a great day.